Hello community, buckle up because this will be a wild ride today. We talk about a brand new topic, pure visual reasoning in artificial intelligence, something that we never had before. We always have to refer back here to a textual logical structure. Not anymore. Welcome to my channel, Discover AI, and we have a look at the latest research paper in artificial intelligence. So let's start. This is the paper, November 26, 2025. Just yesterday it was published here, Peking University, Kling, interesting, and of course MIT. And they develop here a new AI system called Monet, reasoning in latent visual space beyond any image and any language. And I said, yeah, this is the video I want to make. This is fascinating. And I started to read it and I said, okay, so to reason directly within the latent visual space by generating continuous embeddings that function here as an intermediate visual sort. And I said, I have no idea what I just read. This is a paper, I have to tell you, I had to read it twice to just get a glimpse of it. So I decided to go to this paper. So this is the paper before, if you want, Deep Eyes. And this is one of the benchmarks you will see. So if you think this is here the competitor, this was published here May 26, 2025. And this was here by, oh my goodness, here, Peking University and a beautiful incorporation, I suppose, in China. Absolutely fascinating. Deep Eyes incentivize thinking with images via a reinforcement learning process. So you see, we are standing on the shoulders of giants and try to develop further. But my brain was simply not intelligent enough to immediately understand it. I just have pieces, but I could not put together everything. So in this secondary paper, they talked about multi-modal chain of thought in interleaved mode. And I said, heaven's sake, what are they talking about? Coming now back to the papers of today, it is rather easy. They say, we take multimodal LLMs, notice this is an LLM, to generate now some brand new latent embeddings in a new mathematical space that will serve as intermediate visual sorts beyond a textual description and an image embedding. And I just could not get my head around what does this mean? And I tried to build this here. And here you see with Nano Banana Pro. So I said, okay, what do we have? We have an input. And the input is here simply my human query, and so the text and an image. No? This is about here visual augmentation. So I have to give it a text and a query, and this is it. And I have a pixel space and, RGB values for each pixel and everything and linearization, and you notice, no? This is our chain. And now I have a question. I say, okay, so what is the object in the image and where is it located? On the table or maybe on the sofa? What is it? No? So we go here from a pixel space now to a continuous latent manifold. And I understand that we do have here a latent recurrent core. This is the main logic engine here for the visual reasoning process. And this tells us just, yeah, there's a recurrence, and we try to optimize here in this recurrence loop. And I told Nano Banana Pro, hey, build something that looks like here our French ITER, so our fusion experiment, and then we have some braided streams. And yeah, and so if somehow in this continuous latent manifold, the reasoning is happening, then we should have a readout phase where we have the observation 1, the red cube is the object that we wanted to detect, and the observation 2 is the red cube is on the blue surface. So final answer is now back in a human language. The red cube is on the blue surface. So we have now a discrete text output from the query image. But notice, this is completely different to everything that we know. Because we are not doing here a vision language model where we transform back everything into the linguistic textual space here with text tokens. No, we build complete new visual tokens, but in a different way, because we want to reason with them. And this is what I could not understand. Okay, so I had to start from the beginning. I said, okay, what is a visual sort for me personally? And I said, okay, great. So let's take a chair, and now let's rotate this chair in front of my inner eye. And you see, I don't need any text. I just see how the chair now moves, rotates to the left, to a little bit to the right, maybe up and down. I can see this, no? As a human being. But how do you teach an LLM to do this? And then if I want to have a chain of visual sorts, so I want to have the complete reasoning process that we already have established here in textual augmentation, now in visual augmentation and visual only, I have multiple elements, no? But first I have a translation, and then I have a rotation. So you see I have a mathematical operation here of translation, and then the mathematical operation of a rotation, maybe of a mirror image, maybe I want to change the color, maybe I want to change the texture. So you see, I have a chain of visual sorts. So I had now a basic understanding what I'm talking about. And then I thought, okay, we have to perform this as a mathematical operation in a particular mathematical space. And of course, if you go about visual sorts, we have to build a visual space for this, no? Yeah, but it is not any visual space, no? Because just imagine here, if I tell you, hey, imagine the image of a galaxy in our universe, no? A spiral galaxy. And this is what you imagine. You don't need any text for this. You just see it, no? Just to see a beautiful spiral galaxy. Great, yeah. 100 million, 400 million of stars. And then I say, now let the galaxy rotate. And you see that the galaxy is rotating, at least if you have studied astrophysics, you have watched hundreds of hours of videos here, then you see that the galaxy is rotating. You don't need textual description of this. This is a visual process that happens in your brain. Yeah, and hopefully it looks like this, no? The galaxy is rotating. Teach this to an AI. So this visual space, what is this visual space? Now the author tells us, this visual space is generated here already by Vision Transformer, and they went here with the Qixun 2.5 vision language. So this means they took all the images of the internet. I have no idea how many images there are, tens of millions, hundreds of millions, a billion images on the internet. And they trained a Vision Transformer on this, and they have an internal representation space, a mathematical space. This is the visual space that we are going to operate in. So this is now another NanoBanana Pro image that I tried to generate, and you see here in blue, all the blue cubes is now the frozen feature space that is generated here by a Vision Transformer. Note, it is not a convolutional neural net, no. This is now the Vision Transformer space. I have multiple videos on how to build a Vision Transformer in my channel. Just go and search for Vision Transformer. And in this frozen feature space, high dimensional, we have all the geometry features, the shape, the spatial, the volumetrics here, and we have the geometry features, and we have the texture features like edges or gradients or whatever. Everything is stored here in this Vision Transformer, a Qixun 3 2.5 7B model. So this is the mathematical space that we operate in. And now I have here a user input here at A with an image. And now the idea is, generate here the solution. No? And as I showed you, I want here discrete text readout here. The red box is on the blue surface. So how is this happening now in this mathematical space where we just have visual mathematical operations? So somehow we have to get here through this space here, through any particular path. And now, of course, we have to train this path. Yeah? We are an AI, so we have to have a specific training, supervised fine-tuning. And then we have this, let's call it here, this pink, what is it? A tube, pink tube, or the pink tunnel here through this particular space. And then, of course, after supervised fine-tuning, we have a reinforcement learning, alignment, and then this pink tube collapses here to the perfect golden laser beam here, bent here in this particular space, because there's different gravity wells. So we get here to the result. And you see, we have now, we're gonna go for the chain. We have now multiple steps. So the first is here, if you want, that you want to zoom into an image. But we are not gonna build any pixel space. We are not in pixel space. We're not generating any image. We're in a pure mathematical space without pixels. So we have to have a vector representation, an abstract representation that is equivalent to the command zoom in and tell me what you see. And then down the chain, we have a second sort, a visual sort, and this is now rotate. Whatever you see, just rotate it 37 degrees to the left, for example. Angular displacement or whatever. And then maybe you want to scale it, no? So these visual commands are now here in our path. So let's build this. You might say, okay, this sounds interesting from the mathematical side of view because everything that we know will collapse. You can't use anything more or less, no? So let's have a look at the training process. I had to go to the annex to finally understand or grab some idea what is happening here. So what they did, and please start from the annex at first, they authors built an image text interleaved chain of thought training data set. And then I said, oh, now I understand. So what they did, they have a question and an image. No, as I told you. No? Now in this question, they say, consider the initial arrangement of object presented in the image below. You are now required to perform a series of operations in a specific order. So you have, if you want, a chain of sort operation. No? Step 1, eliminate all objects identified as a pyramid. Step 2, eliminate all objects that are blue in color, and then eliminate all objects that are red in color. Then give me what is left. And then this is the training data set. So what they do for each textual augmentation in a chain of thought, they generate here an image. So they have a text to image prompt now, and then they generate an image. And now this here image text interleaved chain of thought. It says the AI will begin by analyzing the initial set of objects shown in the image. They are observation, 7, end of observation, label, distinct object in my initial configuration. My approach will be to systematically apply each removal step and visually track the remaining objects before arriving at the final count. So the first operation requires the removal of all pyramid-shaped objects from the scene. So this means both the purple pyramid and the observed orange pyramid will be taken away. I will generate an image reflecting this change. And it generates now out of the text reasoning an image. So you see, if we go on and on and on, we have here the result. This is here the result. So what we do have exactly like I told you, an image and a text interleaved chain of thought. So we have both. And now imagine we just say, forget about the text, just look at this sequence of images. And this will be helpful for the training of our new AI system. So we have to create new visual states. So the creation of this training data set was an immense task because you had to create images for each and every step. So the author said, okay, so to support here the first step here in a supervised fine-tuning step for our model, we have to construct a training data set, and we call it Monet Supervised Fine-Tuning 125,000. So they really built a high-quality text, image, interleaved chain of thought data set containing 125,000 real worlds, chart, OCR, and geometry chain of thought. My goodness, this is amazing. And then they said, okay, so now that we have it, how do we actually force the AI model to learn now that a specific vector coordinate in our artificial mathematical space equals now to the visual command zoom in and read, I don't know, the name on the badge of this person. Huh? And they said, hey, okay, so we need to visualize now the informational bottleneck that we are encountering. So in the training, in the supervised fine-tuning, and let's go to stage 2 because otherwise it's just filtering. They say now, okay, we can't teach this because this is an AI, and AI is a pattern learning machine. So you know what? We make imitation learning. So we have a huge, massive teacher AI who sees now the pixels, and then we have a little student AI who sees nothing to hallucinate now the correct mathematical formulation of this vector in this artificial mathematical vector space. So what we do, we just force the student AI to learn from the teacher AI. So the quality of the teacher AI is the all-defining parameter here for this learning process. So I will show you now a graphic. So to visualize now 2 parallel neural networks running side by side. The teacher AI is our mainstream now. The teacher AI has the eyes. It sees the actual cropped image, and its internal state is rich and truthful, and it has here the complete pixel space. And the student, just blinded here, sees nothing. Everything is masked out. And now the task of the student is a mathematical optimization process. Just generate some vectors, and we call it latent vectors. And the event is now simply that we have loss function that strike down, forcing now the student's empty vectors, start with 0, to align perfectly with the teacher's rich vectors. So we are just doing a blindfold learning of an AI system in a new latent vector space. I mean, you have to be brave to get to this idea. You say, hey, let AI do the learning. Why should we do this, no? Another Nano Banana Pro image. Here we go. Supervised fine-tuning 2, the most important learning step here. Latent distillation and gradient alignment for a dual-stream neural processing schematic idea that I had. So we have now an image and we want to zoom in, let's say on the eye, or we want to zoom in on a text badge. And there you see it. So for the eye, if we zoom in, we see here the blood vessels here, absolutely beautiful. Or if we zoom in here on the text badge, you see here there's a little chip. Now we have here a full image resolution of this chip. So you see, this is what the teacher AI says, this huge vision language model says, that was trained on all the images on the internet. And then we have here our little student. And our little student here has a masked image input that sees nothing. And now it is here in the training process here. It should learn here an identical information representation like the teacher provides. So we do have a latent representation flow, and we have a particular loss function that is presented here. That you hope that there's a representation alignment here in the loss function or in the force field, and the student comes up here. If this is here the neural activations, that the student here finds the same neural activation and learns here this neural activation, but being blindfolded. Just knowing that this here is the zoom in command. And then the beauty is, and this is the crazy thing I did not get at the very first moment, we are operating still with a large language model. But we are operating now on a mathematical manifold that is strictly a visual latent mathematical space. And I could not understand that it is possible that the LLM operates here not only on its own textual manifold, but in parallel also on the visual manifold. And I said, how is this possible? Yeah, there's a simple trick that you have to understand, and then the puzzle opens up, the box of the Pandora can be resolved. So this means this system was trained in a way that at first, if you give it here the problem to the AI, and you have the text and the image, the AI tries to solve this first on a textual level. And then the AI, learning here 125,000 data, learns that given the, if you want, the linguistic patterns are not complex enough to solve the puzzle, now it activates here the visual reasoning process. Now it says, hey, I have another input data, and this is the image. So let's see if I can deduct from the image here how to come to the solution. So you see, the AI now decides, okay, I have to start and stop here whenever here the textual path is intelligent enough. Only if the text fails, I will activate here the vision reasoning methodology. So we do have a stop gradient here on the text path. So we build now this latent vector for the zoom in command here in the latent visual vector space. How we do this? Okay, let's start from the beginning. I always need the first principle. We have an image. Let's say simplest 224 times 224 pixels. And now, we cut it here in a vector representation into non-overlapping grid of squares. Let's say we have a square that has 14 times 14 pixels. So this gives us exactly 256 squares of our 224 times 224. So we do have a 16 times 16 grid. Remember, this is not a convolutional neural network, but a vision transform architecture. Now, the advantage of a vision transformer is it is just the image is now just a bag of 256 very special tokens. No? And we have the classical attention mechanism from the transformer architecture that allows now the token number 1 to talk directly to token 256 in the very first layer. Now, because the image is now broken into this, now let's say, reduced complexity visual squares or visual patches, we can now have mathematical operations on this. So the image is broken into these discrete patch vectors. This new Monet AI latent sort vector can be constructed and can now say, hey, I want to compare now the information of square 45. This is, let's say, the zoomed in where the dog ear is with the square 200. This is where the tail of the dog is. And let's see what is the color difference. Remember, we are not in pixel space. And this is the crazy thing to wrap your mind around. Of course, if Monet AI would just rotate now one particular latent vector, it would fail miserably. No? Because it's a linear rotation, cannot represent here looking at the back of the chair, because if you turn the chair in the latent vector space, the front legs might hide now the back legs, you have occlusion, you have all geometric artifacts that suddenly come to life, and this is a non-linear geometric change. So this is not the way to go. Instead, Monet takes now the entire cloud of our, or the set of our 256 patches, the complete image, and now does here transformation. So we go here to the MLPs to perform here a complex non-linear transformation on the whole cloud simultaneously. And if you want, it says, hey, if I combine the shape of the left leg patch and the seat patch and apply a 90-degree rotation function, what does the resulting feature map look like? It is not the pixel map, it is the feature map. This is an abstract vector representation. It is a representation of something that has a connex to a pixel space. As I told you, we'll go for the chain of visual sort. So the chain rotation, logical step by step, is in the following. And I'll break down now the complexity. You know, in AI, we always reduce the complexity. We do this here with a textual chain of sort, and we do the same here with a visual chain of sort. So the step 1 is a deconstruction. Huh? We say identify the three-dimensional structure. The model aggregates here the patches to understand that the chair has 4 legs and a high back. It builds here now a mathematical vector space model. If we see the eye as a little human, we see a mental model of this chair, of this object geometry from a 2-dimensional input. Then we have a transformation. This is the next step. And we say rotate the mental model, not in pixel space, but in this abstract vector space, let's say 180 degrees. No? And then, of course, we have a matching. Does the imagined view match now the option B? Or the image is comparable. So it compares now its imagined H2 stage against the actual picture space of the candidate image. This learning process that you teach an AI to do this is something that I've never encountered before, and maybe this was the reason why it was so difficult for me to understand. Just reading here the technical script, which was extremely detailed, but I hope with this video I can open up the complexity of this technical, highly technical paper that you can easily understand it. So, Monet AI operates on the manifold of semantics, not the grid of pixels. Absolutely important to understand. Because simply, Monet doesn't need to know the wood grain texture on how the chair is on the backside. No, the vector space doesn't need to capture the infinite complexity of reality. It only needs to capture the discriminative features, as I've shown you, the blue crystals here, no, required to answer the question. So it all depends here of the domain in your pre-training data set of this model that you really have a lot of low, middle, and high complexity topics embedded or created here in this visual space of a vision transformer. Again, if you have a graphics engine and you do rendering, to draw the back of the chair, you need infinite details, exact wood grain, precise light reflection, the exact shadow angle and everything. Monet doesn't need anything of this, because we don't work in pixel space. we have now an abstract mathematical representation for the reasoning, visual reasoning. So to identify the back of the chair, you only need a topological feature set. This is not easy to understand at the first moment. So Monet just asked, hey, is the backrest closer to the camera than the seat, or are the legs angled away or anything? We are just going for the topological feature map. And given a question and its corresponding image, then Monet AI generates a text latent interleaved reasoning chain. This is a sentence that broke my brain, honestly. I said, wait a minute. So we have a latent visual space, great. And then you tell me that we have a text latent interleaved reasoning chain? Why? I thought we are finally able to do a purely visual reasoning chain. Well, yeah, but remember, there is now a space. And in this space, we have our, our textual tokens. Né? And let's say those textual tokens are in, I don't know, the upper right corner of this huge multidimensional space. But we also have now all the visual interpretation in a complete different area of this space, let's say in the lower left quadrant of this huge mathematical artificial space. So yeah, it is true. We have in this a text latent visual interleaved reasoning chain that we just have to activate. I will give you an example in a minute. So this means, specifically, it can automatically decide, Monet, when to generate now a specific token, like start of latent visual thinking and end of latent visual thinking, to initiate the latent visual reasoning during the inference run. As I told you, default is textual logic, but if it gets too complicated, we have a second input, this is the image, and then activate here the visual reasoning in addition. Now the reasoning complexity of Monet, if you read the paper, was not immediately clear to me. I had to spend quite some time thinking about it. It is limited, of course, by the depth of the network of our system that we use, so the number of layers in our transformer architecture, and the number of the latent steps you're willing to compute. Now, if the physics, because imagine, this sequence here is, of course, based, if we record something, the drop of a water drop is physics, no? There's a gravity, this is a behavior in air, so there's some friction, beautiful. But if the physics, quotation mark, is too hard, like a fluid dynamics of a water splashing out, Monet will of course fail because its internal physics engine, this means the learned weights of just all the images of the world, is not strong enough to simulate this particular sequence, a video sequence here of water splashing out in a vector space. But for rigid bodies like chairs and objects and cars, it works beautifully. This is just the very first idea and the very first implementation. So let's have a look. Monet introduces a new paradigm, and it shifts from the pixel-based tool use in AI to a latent space mental simulation, an internal cognitive simulation of the latent space. And if I say this, you say, hey, is there any connection? Because in my last videos, we talked about an AI dual manifold cognitive architecture. Remember here, when we had this mirror mind paper that we analyzed. And I told you this is now really the attempt to mirror the human mind, all the experience in my last 5 years, for example. And the AI is trying to understand my learning process in the last 5 years of a scientist and wants to create now a digital twin, but a cognitive digital twin. So we deviate from a pure Markovian instruction to a time series dependency of my learning experience. And now we talk about a latent space mental simulation. And yeah, we're all moving in the same direction, but sometimes I don't find here the precise word because this is just a day old for me. So sometimes I'm trying to come up with solutions and presentations to you that I hardly understand in day one. Okay, so what is the method? It replaces here the discrete, underline discrete text image output loop with a recurrent latent continuous loop, allowing the model to perform multiple steps of visual feature aggregation and transformation. So we have simulating the zoom in, we have rotation of the chair, or we search for particular objects in the image itself, entirely within a new mathematical embedding space. It uses here a beautiful distillation pipeline, so supervised fine-tuning here, to teach the model how to use this latent space effectively supervising the sorts, because we have here this teacher AI, this huge, all-knowing, seeing vision language model. And now let's go to reinforcement learning. And here, GRPO fails. So the optimization, so supervised fine-tuning, yes, Jack, but the optimization process, so the reinforcement learning alignment fails. GRPO fails. And you see, of course, GRPO only works on text tokens, on discrete text tokens. We have here continuous visual internal sort tokens. If it's a token at all, it's a vector representation. So of course, GRPO cannot work. And now the absolute beauty and intelligence of the authors was they said, no problem, we built something new, no? We built now a new policy optimization for our model in the pure visual reasoning domain, and we call it VLPO, Visual Latent Policy Optimization. And absolutely, I think it's a real breakthrough that allows now reinforcement learning to optimize here a continuous underline vector sort directly, overcoming the limitation of discrete textual token reinforcement learning with GRPO. Okay, now coming back here. Monet, what it does, it visits here the coordinate of the zoomed in batch, but it doesn't spend energy rendering the pixels, no? So we have here this virtual zoom, the mathematical operation that is happening not in vectors, in pixel space, and the AI is now generating an image to read here. Oh, this is Mr. I don't know, Patrick Smith. No, we do this in an abstract space where we just have here a mathematical or a virtual zoom. Now remember, I told you this is here from the start, our continuous vector or our latent sort chain now here. And I told you this is here supervised fine-tune, beautiful, but we also want to have here the reinforcement learning alignment. And this is here our purple probability tube. And we want to have now, we squeeze the tube now with our alignment function here till we have here the golden, laser band. Now there are a lot of problems you have to encounter, and I will not go into detail for this VLPO tube. Just remember, you really have to reinvent quite a lot of it, but it comes down here how you calculate here the reward functions in our GRPO, because you cannot have you have the probability of the textual token cat, no problem. But if you can't have the probability of a high dimensional, I don't know, 4K vector representation of 0.9782. What is this probability? What is this reward structure? No? So you have to come up with a new distance metric notation in this space. And here they go with a Gaussian policy bound structure. You find all the details in the paper. It is not that complicated. Look, here we have our GRPO optimization process. And this is the formula that you know with here the beta parameter on our Kullback-Leibler term here when we compare to probability distribution. And here our reward structure is here rather simple. But remember, GRPO objective can only be computed on the text token. So what they did, clever, they just optimized this particular term. Look, they say, okay, there's some augmentation for a latent Gaussian distribution. And they say, okay, so now for our VLPO objective, this reward structure is now dependent here on a new, let's say, distant idea in a complex mathematical space, where we have, remember, we have a recurrent, and this is simply they define here a distance step. Simple but elegant. And you know what? It opens up here that we can use now this vision LPO objective for the reinforcement learning alignment process. Okay, this is it. This is it here. Let's look at the result. What do we achieve? I give you here the final results. So here you have it. Benchmark 1, 2, 3, and 4. And we have a GPT-4 Omni model. Okay. Then the Qwen 2.5 Vision Language 7B. This is here the base model if you want. Plus supervised fine-tuning, plus GRPO. And then I showed you at the beginning here the publication of Deep Eyes. No, this was the paper before. And now we have here Monet 7B. So they built this model with the training data set I showed you, and they did this complete supervised fine-tuning and the VLPO. And now let's have a look. So deep eyes is really good. Look at this. I mean, compared to a GPT system, yes, of course. No? But even if you go with for a classical vision language Qwen, 78 to 83, yeah, this is a nice improvement. And our new model is exactly at the same level, 83.25. So compared to deep eyes in this benchmark, it is same performance. If you go here to the next benchmark, we just look at overall, deep eyes is even better, slightly better than this Monet process. If we go to this benchmark, oh yeah, Monet is really better than deep eyes. And here you see, okay, Monet is here winning all the rest of the benchmarks. It is not that clear, but it is absolutely fascinating because remember, we did this here with Monet in a visual reasoning paradigm. The integration of here visual token with DeepEye and Qwen is completely different. And of course, you have seen that I posted already the technical paper of Qwen 3 vision language, which has some brand new innovations, but more about this in a later video. So this is here just to give you about the performance that we achieved after all this abstract visual embeddings and training and interference and test accuracy optimization and everything. But wait a minute, there is something much more important. And the question is, hey, can we now have robots or visual assistants here that think, quotation mark, internally about complex visual scenarios like navigation or medical imaging diagnosis without the massive latency of generating image to check their work? So we go now from, instead of hallucinating pixel in the reasoning process, to hallucinating useful mathematical operations. And I really mean hallucinate because this is at the edge of a probability density function. It is really going into the direction of hallucinating. Remember, this is the very first paper in this. So there are a lot of new ideas. Just to be clear, Monet is not a perfect visual imaged physics engine. Because if you see here, as I told you, a video sequence here of a little water drop falling down because of gravity, this is something that is physics, no? But it is not perfect. It is a probabilistic estimator of a visual physics representation that we try to train the neural network on. It also, again, yeah, I know a probability density distribution, but I'm more on the edge of it hallucinates also the rotation of a chair. But most of the time, this hallucination is correct because statistically, it has seen millions and millions of images of chairs during the pre-training phase. But for normal, out-of-distribution objects, if some crazy designer designed a chair that nobody has ever seen before, this mental rotation might of course fail because it's not in the training data and it is out of distribution. So it relies now on the manifold hypothesis that this mental hallucination is indeed correct, provides correct results. So let's come here to the complexity of the mathematical space and the manifold hypothesis. As I told you, we're not operating here in a discrete mathematical space, but we're operating in a fluid, continuous, smooth mathematical space, and we have complete new algebra. Let's start at the beginning. I always have to go back to the beginning. So imagine a vision encoder. No? A vision encoder is a kind of a librarian organizing here billions of images from the internet. No? And it uses here a mathematical objective called the contrastive loss for the training. So you say to the vision encoder, hey, here's a photo of a dog. And here's the text, a dog. Make their vector representation in this mathematical space almost identical. And then you also have the negative. No, you also have to train on positive images and on negative images. And then you say, here's the photo of a cat. Push its new vector away from the dog vector in this mathematical space. Now, the emergence of fluidity is because the model sees billions of examples and it kind of creates an internal visual representation map in this space where all the dogs are clumped together. It's a cluster of dogs. All the wolves that are relative in the family to dogs are right next to the dogs because they look similar or maybe they have the same heritage. But the cats are further away. The cat cluster is distant from the dogs cluster. Yeah? Beautiful. Now, crucially, it organizes them by the attributes. So you have now images of all the standing dogs on the left side, let's say simplification, of the dog cluster, and you have all the sitting dogs on the right side of the dog cluster. And now if we have a continuous space, the beauty is now the space between the standing dog and the sitting dog becomes now a smooth, continuous gradient of dogs sitting down. You see what we achieved? We don't go in a discrete space, but we go in a smooth, continuous gradients. And this brings us here this beautiful translation, this morphing of a standing dog to a sitting dog. And of course, the data, simply Google provides here the millions and millions and billions of photos of dog in different poses. And if you question why Nano Banana Pro is so powerful, I can't tell you, but I have a hint. It is Google that has access to, let's say, all the images on the internet. So you see, something that OpenAI might not as easily emulate, Google, given its history, simply has an advantage just from the training data. So this means now that a contrastive learning algorithm organizes them in a fluid, structured map of representation in a new mathematical space. So when you show now Monet AI a picture of one specific chair, here's what happens. It has a projection. No? The vision encoder looks at your image of your chair and it calculates, this chair looks like 90% like the millions of front view chairs I saw during my pre-training, but it has the color red of the red object cluster. So the placement, it places now your single image onto a specific coordinate, here a vector x, y, z in a 4,000 dimensional mathematical space in that pre-built giant map of the pre-training data. So somewhere it is located that it is beautifully. Because the map is already built by the vision transformer, the back view of your chair already exists there, theoretically, in this mathematical space. And since it is an ordered quotation mark, it is at a coordinate x plus 5, yz. This broke my brain again. So this means, like we did here in the textual, in the word, when we build here with token, where a token is a word, let's say, where we build here the complete mathematical representation space of all the possible words that we use here in a human language. And then we have simply here the cross-attention mechanism and the transformer layers. Now we do the same, if you want, on the other side of the page, with all the images of the world. And we do a visual reasoning. Heaven's sake. And now you see, imagine now we are this vector, and we build this vision transformer space. Yeah, let's say here, Qixun 3 vision language built this new visual space, where really the back view of your chair already exists in the database, because your chair is a model that was already produced 2 years ago, and the internet has already more than 100 images of your chair from all different directions and angles and lighting and whatever. Every possible image is already in this vector representation of this mathematical space. So therefore, the AI model, Monet, does not need to generate the pixel back view image of your chair, because your back view image of the chair is already in the mathematical space. And it knows this from the pre-training. It just needs to move here your vector for +5 notches here on the x-axis. So just a simple translation of your vector. And this represents now a rotation of 180 degrees. This is the beauty. This is the beauty that you do not do any pixel manipulation in the pixel space. But given that you have this absurd amount of beautiful vector representation of all images that are theoretically possible, remember this is just down to a, what was 16 times 16 pixel structure, you can build up any image. You know what this means? This means that we don't need better cameras or more pixels for better AI reasoning. What we need are better pre-trained vision transformers that build us those mathematical spaces, and we need better path navigators like Monet, so a better latent reasoning algorithm. So the bottleneck is no longer perceiving here the pixels, it's understanding the geometry of the space where we have here the visual meaning encoded. Yeah, I broke my brain again. So, okay. Therefore, now we understand that Monet, and this was a breakthrough for me, is only a trajectory optimizer for a latent navigation task through a pre-existing semantic manifold that is extreme high-dimensional mathematical space that was built particular for this exercise. And it was built by, in our case now, a Qwen 2.5 vision language model, a 7B model, and the teacher model was a 72 billion vision language model. So you see, this is it. You have a trajectory optimizer where you just go to the x+5 position to see your chair rotated 180 degrees, because all the images are already present here in this mathematical space. And I still thought, no, this is not possible. You cannot have infinite images. And then I thought, wait, I make a mistake in my thinking. No? Oh yeah. So again, just hold this thought for a minute. Just have to do something else. So the teacher model who sees here the actually zoomed in image, the cropped, the teacher sees the pixel and the teacher brain, the AI, produces here a specific state vector. Let's call it the vector truth. And our student model, our Monet 7B model, has masked out this zoomed image. No? And as I told you, it has to generate latent vector sort based only on the original full image. And now we just force the student AI on Monet 7B to change its mathematical representation until we achieve that the vector truth from the super AI is more or less exactly what our student model Monet 7B hallucinates the vector sort. You see, it's just an optimization process with an extreme complexity. It is not with an extreme complexity because just the space is extreme complex, but there is here the manifold hypothesis, and I will explain this in 2 minutes' time. So therefore, the result here is that the student learns. Monet learns. If I want to achieve the brain state corresponding of seeing a zoomed-in badge, and I'm blindfolded here on the zoom-in image, I just see the full image, I need now to generate this specific vector coordinates. Because there it is. So it learns to, and I again say, hallucinate a mathematical signature of seeing this detail without needing any visual optics. Human need eyes. They have here, I don't know, a LiDAR or radar or photo-optical sensors. Nothing. It's pure mathematics. So, the student AI Monet is moving and optimizing its own visual reasoning chain of the latent sort in this particular mathematical space. And this mathematical space is the learned world model of the teacher AI of the Qwen 2.5 vision language 72B. So our little student AI Monet is just moving in to the world model that was built by the 72 billion Qwen 2.5 vision language and is there just navigating. So this vision reasoning model needs a big brother that builds the world model with all the billion images that are available on the internet and makes sense out of it. That a picture of a standing dog is right next to the picture of a sitting dog. And Monet is just here a path-finding optimization routine. If you understand this, you read the paper from a complete different framing and you immediately understand it. So what Monet is a latent simulation over a fixed visual manifold. But now this is not as easy, no? Because in reality, I have to tell you, and this is now again a little bit more complex, Monet creates a hybrid visual latent space, no? It is now a continuous vector space where the embeddings carry the visual semantic, the shape, the colors, the spatial relations, everything, rather than the linguistic semantics, no? But remember, we have a language brain in our AI operating. And how the hell is this language brain able to manipulate and calculate and digest here the visual data directly without translating it into words first? I could not understand this. So I was missing a piece. Yeah, manifold hypothesis explained. Okay. as I told you, I had the question. Let's make it this way. I said, does it mean that all the possible images of the world, of the patch, of our image, if I show it here, the image of a chair, are already somewhere in this beautiful vector space by our vision transformers, and we just have to move our vector to go there? Is it really that simple? And the answer was yes. And let me give you an example that I had to laugh to recognizing how stupid I am. Think about a piano. Think of a pre-trained vision transformer. Think of the created mathematical vector space like a grand piano, and now our piano has 4,000 keys. And you would say, why? Every song that can be played in this world already exists on that keyboard. If you have 4,000 keys on your grand piano, you can play every possible song in this world. And this is exactly what happens in the visual reasoning. We have 4,000 dimension in our mathematical space, and we can build every possible visual complexity that can ever exist. And then it suddenly made, aha, now I get it. So the piano builder, of course, didn't write the songs. They just built the keys, this means the dimension of the mathematical space, and the string, this means the feature representation in that space with the training of a vision transformer. The task is now zooming in on that badge of this person is just a specific chord. And rotate the chair is just a specific melody you play on this grand piano with 4,000 keys. So if you want, Monet is the pianist that plays now on this mathematical space. It doesn't build the piano. It is just learning that if it presses these specific keys in this specific order, it produces, if you want, the song of the zoomed in badge. I hope this provides you some clarification. And now you might say, wait a minute, if it is this simple, I mean, at first, why the authors did not put it in their publication, but of course, I understand you wanted to be high sophisticated. I get it. But my goodness, why was it that hard to invent visual reasoning? And now the answer is because 99.9 periodic of that vector space is pure nonsense. Think about a Feynman lecture, when Feynman talked about the space between the atoms, between here the nucleus and the electron spheres. There is almost infinite space. The same is happening here. The manifold. Meaningful images, like real-world chairs, real-world dogs, and all the text, hopefully, this is what we hope for, live on an extremely thin, twisted thread on a manifold inside that giant mathematical space. So we hope we have some extreme constraints, the manifold theorem, that we just have an extreme thin, twisted thread manifold. And we have a huge void around it. And if you move now the vector, as I told you, x plus 5, in a straight line, in a random direction, you step off the thread into what we call static noise, into the nothing. And then you have meaningless mathematical garbage that looks and is nothing, because we left our manifold where the reasoning happens. 99.99% is just nothing. And now the space. This space contains now here the mathematical potential for every meaningful visual variation. For all mathematical operations that likes to zoom in visually, rotate an object in 3D, blur an object, brighten up something, modify the brightness or the whatever, you got the idea. So the input is, your specific image lands now on one specific start coordinate on this particular manifold that was generated here with a vision transformer. And then the Monet is just calculating, based on its pre-training, a vector that says, hey, this location, movement. And the result is that you have the start coordinate and the movement vector, and you find immediately the answer coordinate that represent here the visual patch that is here the result of your mathematical operation, like the back side of the chair. You don't have to produce any pixel in pixel space. This is an extreme acceleration of visual reasoning. This means now that Monet is nothing else than a mathematical optimizer or explorer machine in finding existing location on this very tiny, thin manifold in a hyperdimensional world. Which is just crazy because I have so many ideas how to modify here the metric structure of this world, but this will be in another video. So all the texture features and all the geometric features here. This is why I wanted that NanoBanana Pro creates not a plain two-dimensional field here, but a little bit of a warped field. But yeah, NanoBanana ignored my command and told me, hey, Zero, sorry, buddy, but hey, come on, this is the complexity I can achieve. Okay, but just imagine this tiny little fragile manifold is somehow disturbed, warped around, is here somehow hyperbolic or whatever in the geometric metric. So this is here where we have our causal operations on. Yeah, I want to do a future prediction, but I tell you, hey, this is only, I don't know, a 10% chance where, yeah, you can almost ignore it. But I think in some years, robots will not process this expensive video frame by frame operation. You don't need here a super hyperlink connection from a robot to a cloud center. Because if you process the same information as a latent visual stream, a compressed sort vector in this visual manifold, using here kind of a descendant or optimization of the VLPO algorithm described here, you can allow them to react to the world much faster than human can even see it. And I think this preprint here is the first kind of a blueprint for this particular engine that you move away from a frame-by-frame video analysis, segmentation, identification, modification in pixel space. This gives us a possibility to throw all of this away and go to a higher valued mathematical abstract representation in a new mathematical space that we have to optimize. Oh, this did even make sense to me. So we move here from, you remember OpenAI Strawberry, the 01, where we had suddenly this hidden chain of thought process and 01 was just amazing. Sounds like 100 years ago emotionally. Now we have the same. Monet introduces now, if you want, the same hidden visual state for a chain of thought for an AI perception. To a vision transformer, if you go a little bit more in an explanatory phase, the visual library is nothing than a fluid image vector field. Yeah? So the location of a specific image is just a specific point in this space. If I give you the coordinate here of whatever, a 4K dimensional vector, you are standing right in front of a picture of a golden retriever. And you know what? This fluidity is so beautiful, but it's not discrete anymore. This space is fluid like water. It's not like stepping here on a staircase that we have with the textual tokens. You just can move, I don't know, whatever, minimum amount of inches or whatever is your distance metric here to any other position in the space. And suddenly the golden retriever ear moves slightly. You see, just by moving in this vector space, the image is also just a little bit fluid with, I don't know, now the hairs are a little bit longer, or just a little bit more shiny, or a little bit more gray, or whatever. But this is a continuous operation that gives you here an image that is really here a smooth gradient. So I asked here NanoBanana Pro again to come up with some beautiful ideas. So I told him, it, she, whatever. I have on the one side the discrete linguistic semantics where everything is broken down in words. I have my noun, my verbs, I have functional, I have objects, I have predicates, I sum over it, I have mathematical operations here, I have a smoothing out, I have whatever, you got the idea. So those are fixed blocks, discrete elements in my algebra. And now Monet says, great, let's do this flexible. Let's build a continuous visual manifold. So the images of grass is just here, no? It's a vector field of smooth gradients suddenly because we're not operating here on discrete, but now we are smooth. So we have grass that is a little bit yellow, then we have grass that is a little bit more dark green and then light green. Everything is just flowing and morphing into each other. If we work on this continuous visual manifold, things become so much easier, and Monet is just building this opportunity. And this tells us now, wait, so we do have, so this visualization try to prove to you, and please correct me if I'm wrong, because as I told you, this is day one, the idea that Monet is an interface that allows you a discrete logical processor, an LLM transformer, to act as a controller for a continuous physics engine that is based here on a mathematical space representation of a vision transformer. So we go from discrete only to, hey, whatever you want, we are smooth. And I said, explain this to me. Explain this mathematical operation to me. I still don't get it. I don't really feel it, you know? Okay. So I looked further into this. So I said, okay, so in the text, if I have a complex mathematical space, no, let's make it easy, the basics. I have my text vectors. Let's say they got in the north corner of this complex mathematical space. And they are discrete points, no, little islands. And then I have my vision vectors from the vision transformer, and they gather in the south corner of the space. And they are fluid, swirling cloud and ocean of all the texture and shades and colors of grass. No? I say, okay, so I have two completely beasts and two completely corners. And then it happened. I understood that during the vision language pre-training, you are to somehow, however you build a vision language transformer, you have to use an adapter. You have to use a projection layer. Né? And this is the projection layer that later Monet uses for its recurrent operation. So this bridge, this Monet bridge, is not built by Monet itself, but it is an inherent feature coming from the pre-training of the vision language model. And if I have a deep dive here on Qixun 3, maybe I can show you this. So the bridge is simply that a projector state that takes the visual vector, let's say from the south corner of this complex space, and somehow mathematically drags it towards the north corner. Yes, I do. I'm really scientific today. Sorry, but it's a little bit nerfing. And now the alignment happens. It forces now the vector for the image of a dog to sit right next to the vector for the text word dog. And now you see why we can have an LLM operating here in a mathematical space and doing a pure visual reasoning operation. Because we map them into the identical vector space. We just have an extreme additional complexity with this projection layer, but now an LLM can do the reasoning also in the visual space. And when I thought about this, I said, okay, now I have a feeling for the model, and now I kind of understand what is happening. If you have a better immediate explanation, please leave a comment for the community. I would appreciate a more elegant idea. Maybe in the next days it's going to happen. So this means that the LLM, the large language model, the heads, treat now vision as a foreign language of fluid dynamics and applies its pre-learned logic gates to this foreign language of fluid dynamics. It is amazing that this is working. I'm really blown away that this is working. But just think about the complexity that I used here in this video where I tried to explain this to you and where I tried to understand this on day one. Now you know me, I think, hey, if it's easy, it's not worth the video. So let's do this now and let's have another perspective on this. Let's go from a mathematical, purely mathematical point of view, not my simple explanation. Let's do the framing from the attention mechanism. And of course, we are talking about a cross-attention mechanism. I just fly over this. This is for expert only. If you feel it, great. If not, never mind. Step one is the pull. This is the magnet. This is the surge that happens in this space. No? So what is it? Mathematically, it's simple. The attention is simply the softmax of this operation. No? But careful, not globally, only for our latent vector. So this means the latent vector now acts as a frequency-tuned magnet, if you want. So the action is now this frequency-tuned magnet vector flies now through the image cloud space. And if the magnet is tuned to red, it magnetically, quotation mark, pulls only the red patch vectors towards it. And the blue patches feel no pull at all and stay where they are. You see what I mean? And this is attention explained now on a mathematical, theoretical, physical point of view, if a theoretical physics talks about it. Then we have the harvest. Then we have the output, attention times the values. This is what we operate with in a transformer. No? So this is the stuff that got stuck to the magnet, but just doesn't stay there. You remember the magnet absorbs the information, the knowledge from those patches. So the vector downloads now the details, if you want, the texture, the shape, the edges, everything, color, complete complexity, the visual complexity from the red patch it attracted. It becomes more intelligent, more clever. It adds additional information. And then, if this happened, we have then the reasoning process or the evolution of the thinking process. And then we have a recursive definition. Eh? So what is this? I think this is the most important part, at least in my understanding, that after the magnet absorbs now the data of this particular configuration, let's say red, the magnet itself changes. The magnet became more intelligent, and now it can tune its magnetic frequency to another topic. So the magnet itself changes. This is what the mathematical operation optimizes. No? You become more and more, quotation mark, intelligence, clever, smarter, or you say you just optimize here if you do the optimization process itself. So the internal circuitry of the LLM rewrites now the magnetic frequency. So step one, the magnet said, the task of the magnet was find the red things in this cloud. I said, okay, I found it. Great, I integrated. So I said, I have found the red things, now become a magnet that looks here for, let's say, defects on the thing I just found. So now it goes to the next operation. Maybe it is a rotation. Maybe it is looking for defects. Maybe it is looking for some specific features on these objects. Maybe it checks if there's a rotation symmetry or if there's a charge symmetry or whatever else. You understand? But anyway, how you see it. Now we come back to Earth. The simple truth of this paper, of this beautiful paper is, yeah, okay, we have to explain this a little bit further. Simple truth about approaching in 30 seconds. So imagine we have here an image, yeah? And now the task is visual reasoning. The task is, hey, this is the image of the motor block and just analyze here what's wrong. It's not working. So you have a multi-granularity visual input and you have maybe a textual input. And now the system looks at this. As I told you, generates patches here, 16 times 16 pixel or 14 times 14 pixel, I don't remember. It makes here an analysis, it breaks down this in 256 patches. And this is here whatever, and this is here another whatever. I don't know about the engine here. But you have auxiliary visual crops, details here of this image. And then the system can analyze here not the image in completeness, but each single patch. Hey, is this the way it should be? All this is digitized and comes into our optimization loop here with the supervised fine-tuning happened and the policy optimization here for a continuous thing happened. Remember, we do not have a probability for the term cat, so we do have to build a Gaussian constraint function here for a numeric density, let's put it this way, and everything is happening here. So you condense it further down here from this tube into this golden laser thing, and then if you have the latent vectors and the reasoning is happening, let's say here in this image, you see some oil dripping down, you see, there's the mistake, there should not be oil coming out here of these pipes. In this reasoning that you go, this is okay, this here it happens, these latent vectors are then reinterpreted here into a discrete token. This is a collapse that's happening, and you have here natural language output like discrete observation output generated here successfully by this transformer architecture. This is here visual reasoning that this is a Nano Banana Pro image that tried to have here a practical real-world examples. Make an image of your, just take an image of your engine and ask the AI, hey, what is happening here? And this little drop of oil is detected here with visual reasoning. So I was talking about simple truths before I was interrupted so rudely. So complex reasoning. And it doesn't matter if you go for linguistic reasoning or for visual reasoning. It's just simple attention. The attention mechanism that was defined with attention is all you need, applied iteratively. If you really go down deep, it is still the same attention mechanism that is the workhorse for artificial intelligence. Interesting. But you know what? Visual reasoning, and after to reduce this to our simple level of complexity, you remember we are just doing some translation of the chair and rotation of the chair and maybe an inversion of the chair or mirror images or whatever. It's just a change in the perspective, in the framing. It is not a change in the reality. This is interesting because remember, a textual LLM can hallucinate everything in words. Visual reasoning seems to be a little bit more constrained. But this is just an idea and the proof is still missing. So if you are interested, read the paper and tell me, can you find a mathematical proof that shows us that the hallucination effect in visual reasoning is less than compared to a textual reasoning? I would be highly interested in this result. Okay, I think this is it for the video of today. I think I talked already. Oh my goodness. Okay, I don't want to know how long I talked about, but this is an absolute beautiful paper. I had such problems understanding it at the very first. But if you have a deep dive, if you really try to say, I don't give up, I want to understand this, my solution is always go back to first principle and understand here the most basic terms, and then slowly build up the complexity. So I hope I was able to present this idea to you in a way that you say, hey, this is so simple, beautifully. Now we have visual reasoning. I say thank you for watching, thank you for listening. I hope you had a little bit of fun. I hope there was some new information for you. Maybe you still decide to subscribe. Maybe you even say, hey, wow, I want to become a member of this channel. And anyway, I hope I see you soon in my next video.